Below is the graph of a continuous and differentiable function f(x). Now we're going to choose any two different points on the graph, a of a and b of a, such that f of a equals f of b. For example, those are f of a and f of b. If you look, I'm going to connect those, and I'm going to get line with slope of 0, because f of b equals f of a, so f of b minus f a is 0. The rise is 0. Let's find at least one point between a and b on the curve of y equals fx, for which the slope of the tangent line is also 0. We must have some like this. Why we must have at least one like this? Because this is a special case of the mean value theorem in which m equals 0. So we can see that in this case, f prime of c equals the slope of the tangent line at x equals c, but it also equals m, and m in this case is 0. Conclusion: if f is continuous and differentiable on the closed interval ab, and fa equals fb, then there must be at least one value of x, for example c, between a and b, such that f prime of c is 0. This is a very important issue, because if f is continuous and differentiable, then if f prime c equals 0, it must be a critical number between a and b for the function f of x. And this is Rolle's theorem. Let f be a continuous function on the closed interval ab and differentiable on the open interval ab, and f of a equals f of b. Then there is c greater than a and less than b, such that f prime c equals 0. Example: use Rolle's theorem to show that any even differentiable function has at least one critical point. Let f be an even differentiable function. If it's even, we know that f of negative x equals f of x for all x's. It means that for every x, there is a value c between negative x and x, such that f prime of c equals 0. C is a critical number of the function f, and cfc is a critical point of f. Even I can say a little more than that. Because c is between negative x and x to any x, c has to be 0. Combining the intermediate value theorem with Rolle's theorem. Here is Rolle's theorem. We just learned about that. I would like to recall a special case of the intermediate value theorem that says that if a function is continuous and it changes signs on the closed interval ab, then it has at least one 0 on the interval ab. And here's our example. How many critical points does a differentiable function f have given that f of negative 3 is 2, f of negative 2 is negative 5, f of 0 is 3, f of 1 is 2, f of 2 is negative 2, and f of 3 is 4. I'm highlighted in yellow all the values of the functions which are positive, and in blue the ones that are negative. Because I'm going to start by applying this special case of the IVT, or the intermediate value theorem. Every time that a function changes its sign, because it is a continuous function, there must be at least one 0. By the way, the function is differentiable. It means that it's also continuous. And it means that I can apply the IVT and also Rolle's theorem as I wish. Because there is a change on the interval -3 and -2, there is at least one zero between -3 and -2. Let's call this 0 a, so f of a equals 0. There is at least one zero between -2 and 0. We call that b, so f of b equals 0. The reason is because the function is changing its sign between -2 and 0. Another change of the sign is on the interval 1 and 2. So there is at least one zero between 1 and 2. Let's say that this is c, so f of c equals 0. Then the function changes sign between 2 and 3. So there is at least one zero between 2 and 3. We call it f of d. Now I'm going to apply Rolle's theorem. If you noticed, f of a equals f of b. It means that there is some value between a and b, so the derivative of the function is 0. Because the function is differentiable, this is a critical number. So there is at least one critical number between a and b. But f of b equals f of c. So by Rolle's theorem, there must be at least one value between b and c for which the derivative of the function is 0. This is another critical number. And the same happens here. We can see that there are at least 3 critical points of the function between -3 and 3. They may be more, I don't know, but there are at least 3. We will redo the problem. Now we're just going to plot the points. So I'm just plotting f of -3 equals 2, f of -2 equals -5, f of 0 equals 3, f of 1 equals 2, f of 2 equals -2, and f of 3 equals 4. Now we will follow from left to right, and we will apply the special case of the intermediate value theorem. There is a change in the sign of the function, so there must be at least one zero between -3 and 2. Here's another change, so there must be 0 on the interval -2 and 0. Here's another change, so there must be 1 0 between 1 and 2. And here's another change of the sign of the function, so there is another 0. Now I'm going to apply Rolle's theorem. Because there are two values which are the same, actually 0, there must be at least one critical number between a and b. But here's the same story, so there must be at least one critical number between b and c. And there must be another one between c and d. We can conclude that there are at least critical points as before. Theorem. Let f be a continuous function on the closed interval ab and differentiable on the open interval ab. If the derivative of the function equals 0 for all the values of x's in ab, then f is constant on the interval ab. I'm going to show you this theorem. We are choosing 2 points on the interval ab. One is x sub 1 and the other one is x sub 2. And now we can assume that x sub 1 is less than x sub 2. We are going to apply the mean value theorem from the interval that is between x sub 1, x sub 2. Please don't forget that x sub 1 and x sub 2 are on the interval AB, so the function must be differentiable and continuous on this interval. Now we will take f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1, and we're going to get f prime of c, which equals 0 by the theorem. But obviously, if this is 0, we get easily that f of x sub 2 minus f of x sub 1 is 0, which means that the value of the function at x sub 2 and x sub 1 is the same, or f of x sub 2 equals f of x sub 1. But this is true to any two chosen points between a and b. This is true to all the numbers on the interval AB, which means that the function is a constant function on the interval AB. Please pay attention. We already know that the derivative of the constant function is 0. This theorem says the opposite. It's also true. If the derivative is 0, then the function is the constant function. Theorem. If the derivative of x equals to the derivative of g for all x's in the interval AB, then the function f minus g is constant on AB. Another way to write it is the following. If the derivative of f equals to the derivative of g for all x's in AB, then f equals g plus c for some constant c. This is also very easy to show, so I will define the function h, which is the function f minus the function g. When I differentiate that, I get the derivative of h is the derivative of f minus the derivative of g, which must be 0, because the theorem says that the derivative of f equals to the derivative of g. But this should be familiar from the other theorem. Here is the theorem that we have seen a second ago, but instead of f, I apply this to h. Let h be a continuous function on the closed interval and differentiable on the open interval if the derivative of the function equals to 0 for all x's in AB. Then the function is the constant function. Okay, so when I do this with respect to h, I get that h is the constant function. But if h is the constant function, then I get that f of x minus g of x equals c. Example, I'm going to use this theorem to show that sine to the power of 2x plus cosine to the power of 2x equals 1. If you observe, the theorem is about f minus g being a constant, so I'm going to write sine to the power of 2 of x plus cosine to the power of 2x as sine to the power of 2x minus cosine to the power of 2x. So first I will show this. This is the f, as you can see, and this is the g. And this is going to be constant if I will show that the derivative of f equals to the derivative of g. So we differentiate f, which is sine to the power of 2x, and we get, using the chain rule, 2 sine x cosine x. Now we will differentiate g, which is negative cosine to the power of 2x, and we get, by the chain rule, negative 2 cosine x times negative sine x, but after we simplify, we get 2 cosine x times sine x. We get the condition of the theorem. The condition of the theorem was that the derivatives of f and g are the same. Here's the condition of the theorem. So we know that the difference between f and g is a constant. We call it c. Now we have to show that c is 1. When you see that the difference of two functions is a constant c, it means that to any value of x that I will substitute, I will get that the difference is c. So what I'm going to do now is substitute 0. And I get that sine to the power of 2 of 0 minus cosine to the power of 0, or if you want sine to the power of 0 plus cosine to the power of 0 equals 0 to the power of 2 plus 1 to the power of 2, and this is 1. So not only did I show the theorem, I also know now that this c has to be 1. And I conclude indeed that sine to the power of 2x plus cosine to the power of 2x equals 1.